So, welcome to this session of lecture on we will be continuing with the instantaneous form of Maxwell's equations. So, let us go to the lectures. So, last time we were seeing in the previous lecture the different terms which are relevant in the vector identity, which will we remarked will ultimately take the shape of power conservation. So, this time we are going to see how exactly the terms fit together to manifest itself. So, that the equation manifests itself in the form of the power conservation theorem. So, let me write down the equation. So, this is the equation. So, we saw the expressions of the stored energy, which are the electric stored energy, which is del T of W e. So, the time rate of change of the electric stored energy, the time rate of change of the magnetic stored energy, and the power flow and the power dissipated terms. So, we now say that therefore, this term and this term, these two terms should be the power provided by the sources J in I and M in I. So, let me rearranging the terms once again. So, the left hand side contains the power flow, which is this term, the energy densities of the electric and magnetic fields, the time rate of change, and it contains the power dissipation terms P d. Okay. If I now shift, as we said, that this term contains the term involving the power impressed by the sources or the power. So, this term E in I dot J in I plus H in dot M in I contains the power supplied by the sources. So, then what we can do is that we can put that term for the power supplied by the sources. So, this is the power supplied by J in I, E in I dot J in I, the electric source, the power supplied by the magnetic current source will be H in I dot M in I. So, therefore, the equation is now arranged such that the power flow term P f, the time rate of change of the stored energy, the electric stored energy and the magnetic stored energy, and the power dissipation terms are to the left hand side of the equation. The right hand side of the equation, this contains the power, it contains the power supplied by the sources. So, this is the Okay. So, together with the minus sign. So, this is the statement of the power conservation theorem. It says that the power supplied by the sources must be spent into the power flow term, the time rate of change of the stored electric and magnetic energy densities, and the power dissipated term. So, therefore, we write P s so let us call this equation 22. And we call this equation 23. So, equation 23 basically states that the density of power supplied by the sources must equal that leaving the point. So, this is the term the power leaving the point plus that dissipated, which is this term, plus the rate of increase of stored electric and magnetic energy densities. So, that is those are this term. So, now we will integrate for the whole region. So, this is a point relationship. So, this is a point relationship. Now, we will integrate over the whole region for the entire region of space or for the region of space under consideration. This is the total energy W e in the entire region under consideration. So, we have formed the triple integral because it was the energy density. Similarly, W m becomes W m becomes the stored magnetic energy, and we have derived that from by triple integrating the energy density. So, this is the total electric energy and this is the total magnetic energy. And the net power converted to heat energy will similarly be found P d, big P d. Note that this term is different from this term. This is small w e, this is capital W e. This is small w m, this is capital W m. This is small p d, this is capital P d. So, this is found by performing a triple integration over sigma E in square d tau, which was small p d. So, this is the net power that is converted to heat energy. This is the net power converted to heat energy, or the ohmic loss, the total ohmic loss in the region. Similarly, we can find the net power supplied by the sources in the region. And that will be P s. It is different from small p s, it is different from this term. This is small p s and that is capital P s. So, this is the net power supplied by the sources in the region. The net power supplied by sources within the region it is found by the triple integration of the power density. So, it is found by triple integration of the power density term. So, if we now use these terms into equation 19, which we derived before. So, using these in equation 19, equation 19 can now be written as P s is P f plus d d t of W e plus W m plus P d. Hence, the power supplied by sources within a region, which is this term, must equal to that leaving the region, which is that term, plus that dissipated, which is that term, that is also within the region, plus the rate of increase in electric and magnetic energies stored within that region, which is this term. So, this is the statement of the power conservation in the instantaneous domain. You see the explicit appearance of this term, the time term. Okay. So, this completes the statement of the power conservation in the instantaneous domain. So, we have the power flow terms, the rate of increase of the stored energy term, okay, the power dissipated term and the power supplied term. Now, let us go to the time harmonic form of these same equations. The point form, the integral form, and then graduating to the Poynting vector, the relationship between the instantaneous form and the time harmonic form, and finally, the statement of the power conservation in the time harmonic form. So, we are all aware of the time harmonic notation, but we need to state that here, because we will be using this kind of mathematical language. We use this mathematical language everywhere in electromagnetics in the time harmonic domain. So, we need to first of all clarify what exactly we mean by the time harmonic domain and what are the fundamental mathematical operations in the time harmonic domain. So, we begin with a brief review of complex quantities. We have a voltage V which is expressed as root 2 mod V cos omega t plus alpha, and that is can be written as root 2 real part of V e to the power j omega t where V is mod V e to the power j alpha. So, in this notation, the instantaneous electric field E in can be written as root 2 mod E cos omega t plus alpha, and that is root 2 real part of E exponential to the power j omega t. Where E is consists of the magnitude part and the phase part. So, mod E is the amplitude part and e to the power j alpha is the phase part of E. So, E itself is a complex quantity other than its time variation term e to the power j omega t. So, we also will write some fundamental operations which we use in the complex domain, which is real part of A plus real part of B is real part of A plus B. Real part of alpha A is alpha real part of A, where alpha is a constant. Del x of real part of A real is real part of del A del x integral of real part of A dx is real part of A dx. So, as an example we can write E in dot dl so we can write root 2 real part of V e to the power j omega t. We write V is integral E in dot dl we write V equal to integral E in dot dl and therefore, root 2 real part of V e to the power j omega t equal to root 2 real part of e to the power j omega t integral E dot dl. So, we have cancelling all the e to the power j omega t variation. So, cancelling this term with this term, this with this and this with that, we have V equal to integral E dot dl. Okay. We can similarly write u equal to integral h dot dl. So, what this essentially means is that we are explicitly not mentioning the time variation. So, the time variation, because it is appearing on the left and right side of the equation, the time variation is cancelled on the left and right side of the equation. So, that we do not need to bother about the e to the power j omega t variation. It also happens in low frequency, okay. It is independent of frequency. So, this will happen the same thing will happen at any given frequency. So, we use the time harmonic form and basically we do not need to use the e to the power j omega t term. So, if you look at any paper, they will say that the e to the power j omega t term is suppressed. This term is suppressed. So, then we have by the same token I is equal to j dot ds and k as m dot ds. We call these sets of equations, including the previous one which we wrote in the last slide. So, including this one, so we will put a bracket probably here, and including this one, we call these sets of equation 26. Now, we can also find out the in a similar manner by omitting the time variation, the complex form of the Maxwell's equation. So, the time harmonic form of the Maxwell's equations from equation number 16, and that is curl of E equal to minus m t and curl of H equal to j t. So, we put a vector here. Okay. And we call this equation 27. So, we write curl of E equal to minus m t and curl of H equal to j t. We can call this equation 27. However, consider the equation having the explicit d dt term or del t term. In that case, for example, I have that equation curl of E in we have the equation curl of E in is minus del B in del D. So, we can write this as curl of root 2 real part e to the power j omega t equal to minus del t of root 2 real part of b e to the power j omega t. Therefore, root 2 real part curl of e to the power j omega t. Therefore, root 2 real part curl of e to the power j omega t becomes minus root 2 real part. Because of the del t operation, we pull the j omega term out, say j omega b e to the power j omega t. Therefore, curl of E becomes equal to minus j omega b. So, it simply pulls the minus j omega term out because of the minus sign, this stays at minus sign, and because of the del t operation we get the j omega term here. So, the other equations can be similarly written. So, we will write curl of E as minus j omega b, curl of H as j omega d plus j, divergence of B is 0, and divergence of D is q v. So, from 13 also we can write the complex forms of 13 from equation 13. So, for equation 13 we can write the corresponding complex forms. So, where d equal to epsilon E, B is mu H, J is sigma E. This corresponds to 29. Okay. So, let us stop here, we will continue from here.